Okay. Unsupervised learning. We don't have complete understanding of the data or variables like which is the dependent variable or independent variables. And also no understanding of which algorithm to implement. So in unsupervised learning, we will not have complete understanding of the data or the variables, which can be your dependent variable, which can be your independent variables, and which algorithms to be implemented. That understanding will not be there. Within unsupervised learning, we use clustering techniques like the popular is KMeans clustering, hierarchical clustering, DB scan, etc. So predominantly in unsupervised learning, clustering techniques are used. See, when not every time you will be able to fit algorithms on data. Sometimes you have to simply do a clustering analysis, group the data into clusters, and then you will be providing the analysis to it. So not that every time you will be able to implement machine learning algorithm. Sometimes you have to simply go with a clustering algorithm or a clustering technique and do the analysis. So clustering, as the word suggests, grouping. Clustering, as the word suggests, it is a grouping algorithm. Now, within this, the popular algorithm is K-means. K-means is an iterative algorithm that divides unlabeled data into K different clusters in such a way that each data each data point belongs to only one group or cluster that has similar properties. Unlabeled data will be grouped into K different clusters based on similarity. Now, how is similarity determined? Based on distance. Closest the distance, similar the observations. Closer the distance, similar the observations. So this is the distance-based algorithm. Clustering is a distance-based algorithm. So closer the distance, similar the observation. That is how the grouping will be done. It is a centroid-based algorithm. It is a centroid-based algorithm wherein each cluster will have a centroid, also referred as midpoint or central tendency. Every cluster will have a midpoint or centroid. From that midpoint or centroid, the distance is calculated and the closeness is found, and then accordingly the clusters will be there. It's a centroid-based algorithm. The objective of this algorithm is to minimize sum of distance between data points or observations and corresponding cluster centroids. The loss function is minimize the sum distance. Minimize the sum distance between the centroid and the observations. So this is how the clusterings will be done. Observations will be grouped based on the distance from the centroid. Right? Cluster 1, cluster 2, 3, 4. It will be grouping the observations, and each cluster will have a midpoint or a centroid. Midpoint or a centroid. From an unlabeled or an unstructured data, we are getting a structure here in terms of clusters or grouping. In terms of clusters and grouping, we are getting some sort of analysis. Now, there are two critical tasks. One, the determine the K value. K is an integer value and there is no fixed formula to find the best value of K. It is found through grid search or trial and error. And the second is the distance metric to be used. The distance metric to be used. There are many types of distance, like Euclidean, Manhattan, Canberra, Hamming, etc. So you also need to use the correct or the best distance metric. By default, it is Euclidean. And like in all distance based algorithms, scaling like standard scalar or min-max scalar must be done before running the clustering algorithm. So before running the clustering algorithms, like I told you in all distance-based algorithms, it has to be scaled. Data must be scaled. Okay. Now, if you are looking at distance, so these are the popular distance metrics. Now, Euclidean distance is easy to calculate, they are the best, but it is sensitive to outliers. There is something called value difference metric, that is we don't use. We don't use that much. Minkowski. This is the Minkowski distance to the power of 1 by n. So ordinal and quantitative attributes, if your data is ordinal in nature, ordinal means ranked in nature or it has certain ranking parameter, then we use Minkowski. Cosine, this is very popular in text mining. Cosine, chatbots or recommender systems. Recommendations you get, na? When you search for product on Netflix or Amazon and all. There, cosine similarity is one of the popular metric which is used. Cosine distance is very popular in text mining. Then Pearson correlation, you know the correlation, right? Correlation metric. Mahalanobis distance, this is also very popular, but this has good accuracy, but it requires a little bit of computing. The formula is complex. Mahalanobis distance is widely used in academic research and clinical and pharmaceutical research. And like I told you, one more distance metric which is very popular is Hamming distance. Hamming distance is used in what we call text mining. Hamming distance is used in text mining along with cosine similarity. So this is the formula of Hamming distance. Mismatching, if the same thing is, if both the strings are same, it will be 0. If they are different, it will be taken as 1, and some of those difference will be taken as your distance. Here the distance is 7. Okay, Hamming distance is used in text data along with cosine. Optimal number of clusters. Elbow method. Elbow method is a method which is used to find the optimal number of cluster. Within cluster, sum of squares. WCSS that defines the total variance within a cluster is plotted, and the point at which there is a bend or reduction in variance is considered as optimal value of K. Within cluster sum of squares, which is nothing but the variance between the centroid and the observations, is calculated and it is plotted. Now, if you are looking at the elbow, so once you plot your WCSS and the K values, you will get a plot like this. See, this is the point where you get the optimal number of clusters, the elbow point or the bend. See, there is a huge variance from this point to this point, and there is a variance from this point to this point. After this point onwards, the variance is stagnating. See, they are almost of a similar size. The distance between this and this is similar. This to this is similar. So that means either it reduces or stagnates. Either there will be reduction or stagnation. So this point is considered as the optimal number of cluster. This point is considered as the optimal number of cluster. So you randomly give a value of K, and then build a model, plot the WCSS, you will get the optimal K, the point at which you will see the elbow. Okay. Now, there is one more metric which we use in clustering. If you are still in confusion that whether that clustering is good or bad, whether you are still confused, or you want to check whether your cluster formation is good or not, we have something called Silhouette score. So Silhouette score is one score which will help you to understand So Silhouette coefficient or Silhouette score is a metric used to calculate the goodness of a clustering technique. Silhouette coefficient or a Silhouette score is a metric which we use to find the goodness of it of a clustering techniques. It ranges from -1 to 1. It ranges from -1 to 1. 1 means closer to 1. Closer to 1 means clusters are well apart. Clusters are well apart and clearly distinguished. So typically, closer to 1 means typically 0.50 to 1 is what we look for. 0.5 to 1 is what we look for. That means your clusters are distinct. They are not touching or overlapping on one another. Zero means the distance between clusters is insignificant. That means they are very close to one another. Zero means they are very, very close to one another, almost touching to one another. Minus means the clusters are assigned in the wrong manner. If you get a negative score, that means your clustering process is giving you wrong output. What is the, when I say wrong way, what it can mean? Observations are assigned to wrong cluster, overlapping clusters, overlapping, one on the top of the other or one like your Venn diagram, right? Overlapping clusters and all will happen. Then you get a negative score of your -1. So if you are not sure whether which optimal you are going to take, sometimes you will see multiple bends. So then what we will do is we will build models with all the 3 or 4 points where you see the bend, which you think are the optimal clusters. And the cluster that has the highest Silhouette score will be your final K value. The final K value will be dependent on the Silhouette score. If you are still confused, if you can't identify the optimal point from your elbow method, you take the 3 or 4 point K values, build models, and for each of them calculate the Silhouette score. The one that has the highest Silhouette score will be your best fit cluster or optimum K value. Okay, so initially randomly give something, a number, and then you start plotting the elbow plot, optimal method, find the optimal cluster, or else use optimal elbow method with Silhouette score to find the optimal cluster. All right. Got it? Yeah. I sent you the Excel sheet. Open it. Okay. Now, let us say, assume K is equal to 3. Assume K is equal to 3. And we will be using Euclidean distance. Okay. Now, it's an iterative algorithm. Like I told you, it is a iterative algorithm. Iteration 1, it randomly selects 3 sets of observations as centroids for calculating distance. Now you can see. This projector, we need to do something else. Okay. Which one? I tried it, no? Still it's not working. No, the problem is with projector and the screen. Okay, let's assume it has picked this as your random selection. Randomly, it choose these 3 for your what you call for calculating the distance. Now it will calculate the distance cluster 1, 2, 10. SQRT open bracket this minus this, fix the value because distance from that particular cluster to the power of 2 plus open bracket 10 minus 10 again, fix it to the power of 2. Square root of x2 minus x1 whole square plus y2 minus y1 whole square. You got 0. Now, if I drag the formula down, I'll get the distances for all the observations. Make it 2 decimal. So this is the formula for calculating the distance between the point which is the first centroid is 2 comma 10. So we are using 2 comma 10 to find the distance from all the observations. Okay. Fix the centroid by putting Fn plus F4. Now same process, distance cluster 2, the values are 5 comma 8. So is equal to square root of open 2 brackets plus 5, fix the value Fn F4 the power of 2 plus open bracket minus 8 Fn F4 to the power of 2 close bracket. Now we will drag the formula to the down and make it 2 decimal. Okay. Similarly, distance cluster 3, the observations are 1 comma 2 is equal to SQRT open 2 brackets 2 minus 1 Fn F4 to the power of 2 plus open bracket 10 minus 2 Fn F4 to the power of 2 close bracket. Two decimal settle. Okay. 2 minus 5 whole square plus 10 minus 8 whole square. 2 minus 5, 10 minus 8. 5, 8 are centroids. Got it? This is C3. C3. D2 minus D5, second centroid. Third is D2 minus D8. Got it? Okay. Now, each row's lowest distance. What is the lowest of all these three? 0. So it is cluster 1. Lowest among these three, cluster 3. C3. Lowest among these three, 5. C2. Lowest is C2 again, 0. Here C2 again, 3.61. Here also C2, 4.1. This is C3. This is again C2. Minimum distance will be taken. What happened? Got it? See, you have to remove that in options. Sorry, circular reference. Hey, use this one and remove that size, Tarun. You have to remove that
Yes,
term
sir.
circular referencing, okay?
Yes, sir. Yes, sir.
It will work.
But C2 and C3 are working, sir. Only for C1 it is not coming, sir.
It is D2 minus D2. Now you are doing the same cell formula, right?
Yes, sir. Yes, sir.
C1, we are taking the same formula, same cell minus same cell. That is called circular referencing. So you have to turn it off.
Okay, sir.
There, we are deducting from the same, na? D2 minus D2, right?
Yes, sir. But in C2 also we are doing that same cell to same cell, no, sir. But it is the C2 and C3 are working perfect.
We started with C2 minus C5.
Yeah, sir. Yes.
See, circular referencing happens in the first instance. If the first formula itself is self-referring, we call it as circular reference.
Okay, sir.
Here. Okay.
Yes.
So just find it and remove it. Okay.
Yes, sir.
Now copy the data. copy the data table. Okay. Now, C1, there is only one, right? C1, there is only one observation, 2, 10. So it will be the centroid. Automatic centroid will be 2, 10 because there is only one in the C1. C2, we need to find the centroid. Now, what are C2 values? 1, 2, 3, 4, these 4 values, and this is the 5th value. That means 1, 2, 3, 4 control the 5th value. And if you come down, the average is 6. The average of this 4 is 6. So 6, comma, similarly for the other set 1, 2, 3, 4, and then this one. The average is again 6. The average is again 6. So the new centroid for C2 will be 6. Okay. C3, we have 2 C3s. So that means we have to calculate the fresh centroid for C3. Because we have 2, right? So what are the 2 observations? 2 and 1. Right? So 1.5, comma 5 and 2. 3.5. 3.5 is the centroid. We calculated the centroids based on the allocations. What observations are allocated, those average we have taken. Centroid is nothing but average, right? The mean. So we got the fresh centroids. Initial centroids were random. Initial centroids were random. Now we have calculated centroids based on the cluster allocation. Based on the clusters, we calculated the centroids. In the prior instance, that was randomly selected. The first one will be randomly picked by the algorithm. In the second iteration, we will calculate the centroids based on the cluster assignment. Based on the cluster assignment, we will calculate the new centroids. Now we got the new centroids as 2, 10, 6, 6 and 1.5, comma 3.5. See? C3 we have 2. This and this. C3, this 2, na? 2 and 1. 2 plus 1 divided by 2, 1.5. 3 by 2. This is 5 plus 2, 7. 7 by 2 is 3.5. Average, na? Simple average. Now let us calculate the centroids again. Distance. SQRT 2 minus 2 to the power of 2 plus open bracket 10 minus 10 to the power of 2. Close bracket. 2 minus 2 to the power of 2 plus 10 minus 10 to the power of 2. Drag the distance down, decrease the decimal to 2, center the data points. Similarly, is SQRT, open 2 brackets, 2 minus 6 to the power of 2 plus open bracket 10 minus 6 to the power of 2, close bracket. 2 minus 6 whole square plus 10 minus 6 whole square. Decrease the decimal to 2 and center it. Is equal to SQRT, open 2 brackets, 2 minus 1.5 to the power of 2 plus open bracket 10 minus 3.5 to the power of 2. Close bracket. So for cluster 1, we are minusing from 2 and 10. 2 comma 10. Observation minus 2 plus observation minus 10. All right. Now, minimum is C1, minimum is C3, minimum is C2, this also C2, this also C2, this also C2, C3, oh, we have a change, C1. That means we have to restart the whole calculation again. Till the point when